So let's talk about this required practical investigating the resistance of a wire. So before we go into the required practical, let's just revisit the idea of resistance. So if you just have a quick look at my picture here, this young gentleman here is trying to make his way through the crowd. He is trying to force his way that way and is experiencing a lot of resistance. He's going to find that hard to do that. Same thing with circuits, except when we're talking about resistance, we're talking about how hard is it for charge to flow through a circuit, or I guess a component as well. And that had the unit ohms, OHMS, and it had the symbol that was like that, the omega symbol, and it looked like that. So this is all about working out the resistance of a wire. Let's have a little bit of a quick talk about the equipment, and then we'll talk about variables. So your equipment is going to look a little something like this. So let me talk you through it. Here you've got your ammeter. That's going to measure current. Now it doesn't really matter where you place your ammeter. That says anmeter. Let's try that again. Ammeter. It doesn't really matter where you place your ammeter, because remember, current is the same at all points in a circuit. It's a series circuit. We'll talk about that a different day. Over here I have a battery. This is going to be my source of potential difference, and that's going to get my current flowing. Here I have a switch, so I can turn this experiment on and off. Here I have a voltmeter for measuring potential difference. The more accurate name for voltage. This thing here, well, that's a ruler, a meter ruler. You can see I've drawn the numbers on with my usual accuracy and precision. And this red thing here is a wire. Oh, and one last little bit I need to add. There we go. I've got some crocodile clips added on as well. So these are crocodile clips. Here and there. Okay, so let's talk about what this is going to do. When you close the switch, what's going to happen is that current will start to flow. It will flow along the wires, and then it will flow along this wire that's attached to the ruler, back up here and back to your battery. Obviously the switch has got to be closed for this to work. What that will do is it will give you a reading on your ammeter and your voltmeter. So you can say at 80 centimeters along this ruler, the reading on the ammeter is so many amps and the reading on the voltmeter is so many volts. What you can then do is you can then adjust where one of the crocodile clips is. So what you can do, let me just remove that label to make things a little bit clearer what I'm up to, is you can shift that crocodile clip further along. It's turned up there anyway, just ignore that. So now when you switch the switch, current will flow, and it will flow along this wire, but do you see that the wire is only 40 centimeters long? It is half the length. So this investigation is all about how does that affect the resistance. Now, a couple of things to note. Ammeter in series, as ammeters should be. They've got to be part of the flow to measure it. And voltmeters, because of the voltmeter, because it needs to be measuring the potential difference, the difference between two places, that has to be plugged in parallel, because it needs to show the difference between two places. Now, what you don't want to do is you don't want to add your voltmeter over here across the battery, because all that's going to do is tell you the potential difference from the battery, which will be the, if you like, the maximum possible value. What you want here is you want the just the potential difference along this bit of wire which you are changing the length of. So you have tried a lot of different lengths and you have recorded some results. But what about the variables? What things need to be dealt with? Well, your independent variable here so the thing that you are changing on purpose, well, that is going to be the wire length. The dependent variable well, that's the result that you're measuring. Well, what we're going to do is we're going to measure the current and the potential difference, and we're going to calculate resistance from that. We'll talk more about how to do that in a second. In terms of control variables, there are a couple of really important ones. First of all, the wire needs to be the same thickness. That needs to be controlled, so no swapping it out for another one. The other really important thing is the wire temperature. Right. For reasons that we'll talk about in a minute, when a current flows through a wire, there is a heating effect on the wire, and that increases its resistance. And the hotter the wire gets, the more resistance it has. So you are adding in an extra variable if you're not controlling the wire temperature. This is what the switch is for, because what you want is you want it on for the minimum possible time. So basically what you want is you want to switch this on, get your readings and switch it off before the wire starts to heat, because that's going to introduce another variable. We'll talk about why that is a problem later on. So you've done your experiments, you've repeated it at lots of different distances, you've repeated each distance a couple of times, you've got some combinations then of length of wire, ammeter and current from the ammeter and the potential difference from the voltmeter. You then need to use our friend from the last time we talked, which was V equals I times R. Potential difference is current times resistance, and that needs rearranging a little bit, so let's just do a quick equations triangle. We've got V at the top, I down here, and R just there. I'm trying to work out resistance, so that's going to be V over I. So resistance equals V divided by I. So that being said, you've now got combinations of resistances, which you worked out using these equations, and lengths of the wire. What then? Well, you can then draw yourself a graph. Where has my graph gone? So, yeah, you can draw yourself a graph with length of the wire along the bottom and resistance up the side. And if you draw this, you will probably get a line that looks a little something like that. It should be nice and straight. So things to note about this. First of all, it should pass through the origin, because if the length of the wire is 0, if the wire basically doesn't exist, then it should have a resistance of 0 ohms, because things that don't exist shouldn't have any resistance. The wire should be nice and straight, because these two things are directly proportional. That means if you double the length, then the resistance will double also. Now, this is only true if you've managed to keep the wire temperature under control. Now, we'll talk more about that in the next video, but it's really, really important. If you haven't got a straight line like that, it suggests that perhaps your wire was starting to heat up and its resistance was changing as the experiment went on. So you could even do the same distance, like 40 centimeters, you could do it a couple of times, and if the wire's heating up all the time, well, the resistance won't be the same each time, even though the length will be. So why is this then? Let's just have a quick talk about why are we getting this situation then where wire, the longer it gets, the higher the resistance is. Well, that's quite an interesting little story in itself. So let's just do a quick bit of modelling. So let's assume that this here is the metal inside a wire. What you've got here is you have essentially metal ions. Now, what do I mean by metal ions? Well, the thing about metals, and that's what makes them a conductor, is that you have the nucleus, I'll just put N for nucleus here, and you have their electrons which orbit around the outside of them, like so. But the special thing about the outer shell electrons of a metal is that they can wander off, they can delocalize. And if there is a source of potential difference, you can start to get them to flow. So there's an electron, there's an electron, there's an electron. If I apply some potential difference, I can get them to start flowing this way. Okay, so as they're flowing this way, these electrons, I'll just label that electron, are going to bounce off these ions. They're going to come along, bounce, and they're going to get bounce, bounce, all the way through. Each collision is going to release some energy all the way through. This is why a current flowing through a wire has a heating effect, you see. Now, the easiest way I find to imagine this is if you imagine a corridor, okay? And let's say you have a corridor full of people. There is a person, perhaps they're having a conversation, and there is another person, and another person, and another person. And you are going to try and fight your way through this corridor. Perhaps you're late. This looks like a tube station tunnel, so maybe your train's about to leave. You barrel down the corridor and you bounce off all these people, slowing down. They're slowing you down and making you lose energy as you run. If you make that corridor longer, so you have twice as far to go, that is going to make the resistance higher. So if you think about it this way, if you're trying to go down this corridor to get to your train, and the corridor goes on for twice as long with all these people standing around, it's going to be that much more difficult for you to reach your train. I went on about thickness as well, thickness of the wire. If the thickness of a wire goes up, its resistance goes down. You want to think about it this way: when you are trying to get through this crowd of people in your tube tunnel, you have more options to get through. You have more places that you can squeeze through, and it's the same thing with electrons. There's a little bit more room for them to try and flow through. Now, I keep banging on about temperature because temperature is the really important one here and will completely foul up your experiment if you let the temperature of the wire rise. If the temperature goes up, what happens essentially is that these annoying people start moving from side to side. They don't get any bigger, but they do start to occupy more room. Now, back in my model up here with my metal ions, that means that these are essentially going to vibrate. They are going to take up more space. They're going to make a collision between an electron and an ion that much more likely. So that means if the temperature is going up, you're going to get an increase in resistance, which, seeing as the only thing you are supposed to be changing in this experiment is the length, and the temperature is definitely supposed to be in control, letting the temperature of the wire go up is a definite no-no. Okay? So, recapping very quickly then, you are going to do an experiment, or you have done an experiment to do with resistance. You're going to change the wire length and measure the resistance. You've got a setup like this with a wire along a ruler, and you shift crocodile clips along, and you take measurements of current and potential difference. You plug them into our very familiar equation over here, and you get some resistances and some lengths. And when you put them together onto a graph, you get a nice straight line because those two values should be directly proportional. Why is this so? Well, metal atoms lose their electrons to become ions, and those electrons try and flow through a metal when there is a source of potential difference. They will collide with the ions, losing energy as they go. If you make that path they have to go longer, that will obviously make it more difficult and up the resistance. If you make the wire thicker, that makes the resistance go down because there's almost like more room for them to move through. But the really critical one, don't let the temperature of the wire go up because it makes the ions vibrate, take up more room. They don't get bigger, they just vibrate and take up more room. And that makes a collision much more likely. That will mean that the resistance goes up too. Cool. Thank you very much.